All right, here we go. Unit numero cinco. So, in terms of kinetics, when a reactant's being used up over time, its rate, the reactant is going to be negative, the product is going to be positive. Because I'm using reactants, I'm making products. Given the following equation, describe kinetics of the reaction in terms of all reactants and products over that time. The first is done for you. So, for every 4 moles of this is going down by a fourth. So that means this one is going to be going down by negative 1/5. O2 over triangle T. This one is going to be going up by 1/6. H2O over triangle T, and this one's going to be going up by 1/4 NO over triangle T. So, crushing a solid reactant, how is it going to affect the rate? It's going to make the rate increase. Why? Surface area. If you crush...
Billy Johnson, if you are in the building, your van is out front.
If you crush a cube of sugar, it's going to dissolve a lot faster than a cube of sugar. Addition of a catalyst. Increase. We talked about this. First of all, this lowers activation energy. Increasing pressure in which a reaction, in which a gas is involved, I would say this could be either. This is going to shift to side with least moles of gas. Increasing pressure in a reaction with only liquids and or solids, none. Why? Pure liquids, pure solids not included. Decreasing temperature usually is going to slow it down. Why? Remember, we're not talking about equilibrium here. We're talking about reaction rates. Particles slow down, therefore less collisions. Decreasing concentration, it's going to slow down. Why? Once again, the reactants / particles are farther apart, therefore less collisions. There's less ions floating in solution. Okay. Page 2. Circle the correct phase. The order of reaction is determined by comparing reaction rates. At the start, when the reaction is at equilibrium, or at the end. So take a second, circle your answer. Reaction rates are only based off of reactants. For the below reaction, the experimentally determined rate law is rate equals K, I to the 1, it's not showing, S2O8 to the 1 as well. In one trial, the concentration of I is tripled while the concentration is held constant. How will this affect the rate of reaction? Well, if the concentration of I is tripled while this is held constant, these were both first order. So, if one is tripled, right, then the rate will triple because it's first order. Now, if it was second order, if one was tripled, one would go times 9 to the 9th. The chart contains experimental data for the following reaction. Which 2 trials will you use to figure out the order for ClO2? Well, for ClO2, in order to figure out the order for that, I'm going to probably be looking at trials 1 and trials 3. Why? Well, it doubles here. This is staying constant, and my rate is changing. So I would use trial 1 and 3. Which 2 trials we use to figure out the order for OH minus? Well, OH minus is changing. I'll do triangle for this one, from here to here. This is staying constant, and this is changing. So I'm going to use trials 1 and 2 for OH. So remember, in order to figure out, you have to hold the one constant while the other one is changing. So this is staying the same while my OH is changing. On the first one, this was changing while this was staying the same. Okay, flip the page. Give the rate law expression for this reaction. What is the order of each reactant? So for this, how am I going to do that? Well, if I look back to the previous page, here is my reaction. So I'm going to write my, let's see, ClO2. On the page. ClO2 doubled, and my rate went up by a factor of 4. So that means 2 to the x equals 4, so x equals 2. Therefore, this is second order. My OH minus doubled, while this went up by a factor of 2. So that means 2 to the x equals 2. Therefore, x equals 1. So OH minus is first order. You guys remember doing that to figure out what the order of stuff is. What's the overall order of the reaction? Well, 2 plus 1 equals third order. What's the rate law? Rate equals K, concentration of ClO2 to the second, times OH minus to the first. We don't write first. What are the units for K? So when you remember when you're doing this, you have to sub in a trial. So I have, this is molar, and this is molar per second. So that means I have molar per second equals K times molar squared times molar. So molar per second equals K molar cubed. If I divide over by molar cubed, I end up getting 1 over molar squared times seconds, or molar -2 second -1. Either one of those would be okay. What is the value of K? You pick any one trial and you're going to sub in your numbers. I usually just pick the first trial. So I'm going to say rate equals K ClO2 squared times OH. Sub in my numbers, 0.131 from right here equals K times 0.002 squared times 0.01. I'll give you a second to solve that. Pause, solve for your K. I got 3.28 times 10 to the 6 for my K. What is the rate of trial 5? So for trial 5, you're going to have rate equals your 3.28 times 10 to the 6, that's my K, times my 0.024, that's a 4 not 5, squared, times 0.015. So all I had to do is just multiply all these together, because the rate is what I'm solving for. So do that, pause, see what your answer is, see if it's the same as mine. Rate equals 28.3 molar per second. Okay, so complete the following table of units for K based on the reaction order. So if it is 0 order, it's just going to be the same molars per second. Units for K. Units for rate are also going to be molar per second. First order, 1 over seconds, or seconds to negative first for K. Units per rate, always molar per second. Second order, you go 1 over both. So it's 1 over molar seconds. Or you could say m negative 1, s negative 1. And my rate is still m per second. As the temperature increases, the K will increase. Remember, temperature is the only thing that can really change your K. If it's at a constant temperature, K stays the same. Flip it. Okay, so I got graphs below. Which graph indicates a 0, first and second? So here I have natural log of A versus time. So this is obviously first order. Here I have A versus time, straight line. So this is 0 order. And here I have 1 over A versus time. So this is going to be second order. Graph the following data in your graphing calculator to determine the order of reaction, A to B. Draw a sketch of the graph that reveals the order of reaction and include the appropriate X and Y labels. So first of all, let's graph this. I would suggest you do this on your own. So remember how to do this. I go into, let's see, stat, edit. L1 is always my time, so 0, 10, 20, 30, 40, 50, enter. L2, I just put it in to see if it's 0 order, 0.525, 0.445, 0.405, 0.375, 0.290, 0.235. Graph, stat, calc. Oh no, I go to graph, and then I go to zoom 9. Okay, that looks interesting. So that's kind of straight. Now let's check if I make it first order. So edit. I'm going to go to L2, enter, second insert, natural log of all those. Graph, zoom 9. I'm sorry, just zoom 9. Zoom 9. All right, that does not look super great. Oh, you know what we probably should have done? We probably should have checked our R squared value. Shoot. Stat, calc, 4. So for this one, I guess it just gives you A and B. I feel like the first one looked straighter. Let's do the last one. Stat, edit, L2, edit. Second insert, second E to get it back to the original. And now I want to do second insert. Whoops, what did I just do? Yikes, 6. Get rid of that. Delete. What did I do? Stat, edit. Okay, here we go. L2, enter, second insert, 1 divided by graph, zoom 9. Graph, zoom 9. All right, well, that's definitely not straight. So it's between 1 and 2. I'm pretty sure the first one looked better. And if you can get an R squared value, I will tell you that it was first order. So that means that this is going to be concentration, I'm sorry, 0 order, not first order. Concentration of A, time, that gave me the most straight line. It wasn't perfect. So my order is 0, which we have never had one. Y, because it was a straight line. So rate equals K. Units for K are super easy, molar per second. Value of K, so I'm going to go to my stat, calc, for, enter, syntax. I'll get rid of that 9, clear. Stat, calc, for, enter. So A is my slope, 0.044, 0.0445. So it's 0.044, and my units are just going to be molars per second. So that's interesting because that was actually a 0 order and not a first or second order. Never had one like that, but that's the process. So, here's the answer key. They actually show how it gives r squared. When you're graphing this, this is what it looked like. I wasn't even looking at the answer key. If it gives you an r squared, whichever r squared is closest to 1 is going to be your answer. So they did all 3, just like we did, and just get the best r squared value. That's how they made first order. Okay, sweet. That's what I said. The half-life of the radioactive decay process is going to increase, decrease, or stay the same over the course of a reaction. Well, half-lives are always constant. Radioactive decay processes are always 0 first or second order reactions. These are always first order. So if I'm studying 2 radioactive isotopes, A and B, the rate constant for A is 0.05, the rate constant for B, so sorry, is 0.1 second. Which species has a longer half-life? Well, my rate constant for A is 0.05, and my rate constant for B is 0.1. So conceptually, A does. Why? So sorry. Because as K decreases, comma, I would say that half-life increases. And we have K, it got smaller here than here. The data below represent a radioactive decay. Using your graphing calculator to graph the data, sketch the graph below, include the appropriate Y and X labels. Man, this is a lot of graphing. Okay, it's good practice though. So graph, stat, edit, time, 0, 25, 0, 25, 50, 75, 100, 125, 150, 175. Over here, on list 2, I have 100, 50, 25, 12.5, 6.25, 3.13, 1.56, 0.781. Graph. Zoom. 9. Oops. Graph. Just graph. I seem to go to zoom. 9. Oh yeah, that's a nice decay series. So sketch your graph below. Here I'm going to have mass. Here I'm going to have years. And it looks kind of like this, which is what you would expect for a nuclear decay equation. So, what is, if I flip the page, using your graphing calculator, determine the order of the reaction involved in the radioactive decay. So, that would have been if it was a 0 order. So I'm going to go back to stat, edit. Now I'm going to hit enter. I'm going to go up to L2, enter, second insert, natural log, graph, zoom 9. Oops. I need to go to zoom 9. Oh yeah, that's a straight line. So that means that the natural log of 90 SR versus time is a straight line. Therefore, what's the order of this reaction? First order. What are the units? First order is always units times the -1. How is the value for the rate constant k determined using the graph? Well, k equals negative slope from the little half sheet that I gave you. So, how long will it take for 75% of the sample to decompose? Show your work. Well, there's a couple ways you can do this. We can do it like this. So if we're using the integrated rate law, we know that T1/2 equals 0.693 divided by K. So 75% of the sample is going to decompose when? Well, I started here, grams remaining, so is that 100? So there's 25 remaining. I don't know. 25 grams. I have 100. How long will it take for 75% of the sample to decompose? Well, first of all, what's my half-life? I have 50% left. About here. So if I follow that down, this is what? 10,000? So am I looking at the right graph? Using the graph to determine sketch the graph. Yeah, we're on something new here. Oh wait, are we not? No, we're still we're here now. So following this down, I've got like this is 10,000 years, so 2, 4, 6,000 years. So that means that 6,000, my half-life equals 0.693 divided by K. I'm going to solve for K. So K is going to equal something small. It's going to be 0.693 divided by 6,000. So that gives me 1 point, I don't know if I'm rounding, 2 times 10 to the -4th, seconds to the -1. Oh, not seconds, that's years. Whatever, years. Now I'm going to sub that into my integrated rate law. Natural log of A at T minus natural log of A naught equals negative KT. So when I substitute stuff in, I know that my A naught is 100 grams because I started at 100. my AT is going to be 25 grams in order to have 75% left. So I'm going to sub in my stuff now. So natural log of 25 minus natural log of 100 equals negative 1.2 times 10 to the negative fourth. Solve and you end up getting, pause if you want to, 11,552 years, which equals t. With sig digs, it would be 1.6 times 10 to the fourth years. That was a little confusing because I wasn't sure if we were doing this one or the one before, but we were definitely doing carbon-14. Okay. Flip the page. What is an elementary reaction? Elementary. A one-step reaction. So for all elementary reactions, the coefficient of the reactant represents the order of the reactant. So for each of the following elementary reactions, complete the table. The first row is filled in as an example. So if rate equals KAB, A plus B yields product, that is bimolecular. Rate equals Ka, A goes to product. We've done this before. That's unimolecular. A squared, A plus A goes to product. That is bimolecular. I know I'm going fast, but you guys can slow this down. I just don't want to have to watch hours of video. This would be 2A plus B goes to product. So I have 1, 2, 3, which is going to be T-E-R, molecular. And then here, A plus B plus C goes to product. So that is also molecular. What type of reaction is most rare? We've talked about this. It's termolecular. Why? Because 3 molecules must collide at the same time. And that is most likely not going to happen very well. Okay, let's just finish this page really quick. Circle the word phrase for each of the sentence. As the concentration of the reactant increases, the rate will increase. Increased concentration means there is a greater chance the molecules will collide. When molecules collide, the kinetic energy is converted into potential energy to break the bonds and rearrange. As the temperature of the reaction increases, the number of collision increases due to an increase in kinetic energy. The energy that reactants must achieve is called EA, activation energy. Activation energy. In addition to the necessary energy, orientation, how they are arranged, is another factor that can determine whether reactants form products. So, the activation energy is 30. One molecule AB collides with one atom with 20 kilojoules of energy. What will happen? Nothing, right? So, they will bounce off each other. Not enough activation energy. Consider the reaction AB to C. Gives me BC plus A. The model on the right shows C collides with B to break the AB bond and form the BC bond. During the reaction, one molecule of C hits the A atom in a molecule of AB. What happens? Well, if I look here, C runs into B. What happens? C is going to bounce off of AB. C bounces off of AB. There's no reaction. Why? Well, not proper orientation. So they have to be ordered in the right way. That leaves us 1, 2, 3, 4, 5, 6, 7, 8. Oh, geez. Well, that's good for part 1.